Welcome to another video explaining the universe using the particle model. Today's video is titled TPM Equations. It's a continuation of videos I'm doing on equations. And today it's about a AC signal generator with just a simple resistor. I've been going over a list of words. I've done space, time, and now a whole series on equations. And my next one will be with an RC adding a capacitor to the AC circuit. Now this is as simple as it gets. This is a signal generator, or you could call it an AC power supply, and it's generally represented with a sine wave. And this is a curve for a sine wave, and it has a positive cycle and a negative cycle. If you were to add up all of these together, you'll get a value, and then you add up these, but because they're negative, it all balances out. The average value of an AC signal that follows a pure sine wave is 0. Measuring voltages and getting 0 for an answer in this case is just not acceptable. So there are other ways that they have found it. This is the same circuit, a signal generator, a resistor, and in this case it has a peak value. And there are two other ways to think about the value. What about an average? Average over a half cycle. What about the average over a full cycle? Well, the average over a half cycle is simply you take the only 180 degrees. Take the half cycle, you add those values, divide by 180, and you get a value of 0.637 times the value of the peak. That's an average for the half wave. The only way they get average for the full wave is use a value they called RMS, or root mean square, and I'll cover that in a moment. And it turns out that its value is equal to 0.707, a little bit bigger than this one. But the question is, well, what in the world is how do you get the RMS value? And we do it by fixing this negative. You got to get rid of the negative because it's just going to be 0 again. So what is done, you square each value of the sine wave. And this is for both positive and negative side of the sine wave. That by squaring it, it gets rid of the negative. Nice, neat little trick. You add them together and divide by the number of samples, which, for example, would be 360 degrees for a full wave. Then you take the square root of that, and you get volts RMS, or root mean squared. So square of the first angle 1, angle 2, all the way out to angle 360. You square them, divide by 360, and you get this 0.707 times the peak. I didn't show the peak, apologize, but that's how you fix it, because they want to use the sine wave in the calculations, but you can't measure voltage and just take the average because it's 0. But if your meter does the RMS value, you get this particular value. Okay, steady state waveforms. Then there's your voltage. And then current. Well, current is a calculated value. I've said this over and over again, whether it's DC or AC. You have to measure the voltage, measure the resistance, divide the voltage by resistance, and you get the current. And in the case of a simple resistor circuit, the current is in phase, exactly in phase with it. And you can measure or calculate the RMS value of current by using the technique of the summing all the squares and dividing by the samples, etc. Well, in the particle model, that's not the way things happen in a particle model. Here's a DC circuit, and I've covered this before, and it kind of goes counterclockwise because the electron or G1 particle leaves the negative side and it travels around this way and it stabilizes, but the voltage or direct current is steady state. Well, in the case of AC, the first half cycle is counterclockwise. It goes this way, and alternating, in an alternating sense, the other half goes clockwise. And they're both positive. So this is the waveform. It's just that one direction is clockwise, the other direction is counterclockwise. And now this isn't the same. It says sine x. I picked this up, and this isn't really a sine x function. The half wave is. So that's the way the current, the G1s flow, clockwise and counterclock, not plus and minus. Well, here's a spreadsheet I did at my very last video on DC. And if you remember, it was really a rather complicated thing, but I took a 10-volt DC source and a 10-ohm resistor, and I calculated what the values were going to be. And I forced the value of G1s to be the same as the number of electrons that pass at one point in the circuit, giving you 1 amp. That's one of the definitions of current, that 1 amp is 1 coulomb of charge passing a point in the circuit in 1 second. So I picked this number 0.1, I adjusted this number 1.6 times 10 to the minus 9th until I got the same number as they got. So I have an equivalent number for the DC circuit. And when I did, when I set it to 0.1, each cycle was 1 nanosecond, and I adjusted IF until I got that value. And the number of particles, the base number of particles going around the circuit all the time, 6.24 billion in each 1 nanosecond cycle. I covered that last time. I'll give you the link to the video in the description of this one when you read it. Well, I also did one for the AC spreadsheet. Now, it's a little different. Yeah, I have 10 volts RMS, but the peak, and yeah, I did a little sneaky trick here. I made the peak equal to 10 divided by 0.707, so that the RMS is 10 volts, a resistor is 10 ohms, and I fixed this as 0.1, and at 1.6 times 10 to the minus 9th, made it the same as the DC, because I want to compare what the value of A is. Well, so I ran the spreadsheet. Now it's a little bit different. I needed to have each degree stabilized. I set it to an angle. I let it stabilize. I pre-calculate, and when it reaches 1, it's stable. And so I find the value of A here, set it to another angle, do the same thing. And when I got all done, I ended up having to do, for the half cycle, so all I'm doing is a half cycle, because the TPM model has 2 positive half cycles, so I only need to do it for 1 half cycle. And I actually did it for 180 degrees, but there are 5 entries, so I had a 900-row spreadsheet doing the calculation, and I ended up with a peak of 8.8 billion at the peak, and the peak is at 90 degrees, not 180, because it went up, and then down. So it's at 90 degrees. And I didn't display it here because that's 900 rows for crying out loud. But that's what the value was. So I also calculated, this is the same spreadsheet, only over a different set of columns. This is the voltage across a resistor. I squared the voltage. I'm doing the RMS of the voltage around the resistor. And I only took every fifth one. Once it was stable, I took that voltage, and I added all of them up, 108, and I got 18,000. You have to divide the 18,000 by 180. This is the way you do. You take 180 samples, you divide by 180, then take the square root of the result. Well, the result of dividing that ended up being a square root of being 10 volts RMS. Yeah, I got a little bit of off here because my value for pi is not precise. So I don't get exactly the right value, but in principle you can see that I got 10 volts RMS for a peak voltage of 14.142. So yeah, so this is you got a half cycle this way and a half cycle this way. The peak was 8.8 billion. The average value actually turns out 6.241 billion. And that occurred, I found that by looking at, I found it at 45 degrees in my spreadsheet. So you compare what the voltage, the peak voltage for both is the same. The average, if you just take the simple average for a sine wave, it's 0. Volts RMS, yeah, it turns out that you can do a full wave and square all the voltages and add them together, divide by the samples and root that, and yeah, you get 10 volts. In this case, I was only doing a half wave. The peak is 14.142. The average is only 9, but the ratio for the average of volt average 9 over volt peak is that simple 637. So I verified with the spreadsheet that an average value of this curve is in fact 0.637, which is what was indicated earlier, and the RMS value is the same. So we get similar answers, but we're doing it a slightly different way. Now here's just a final one with a different waveform. This waveform is a composite of a primary frequency and a third harmonic. And the third harmonic is divided by 3. This is a typical way you start to analyze a square wave. You have a primary frequency, 1 cycle, that's the sine A, and then 1/3 of the harmonic, that's this little guy, and there's 3 full sine waves in one of the other one, the larger one. You add them together and you get this shape. So if you're going to analyze this waveform, I'm analyzing the composite waveform. Looks like a tooth. It's going to be average 0 again because you got positive values and negative values that are equal. Yes, you can calculate the RMS of this, but you really have to use calculus. And I haven't done calculus in a long time. So I'll let those two people who do that. Well, I used my spreadsheet to calculate the average, and yeah, I got the 10 volts. But the RMS value is not 10. Now, remember, this is a sum of 2. The primary one would be just 10, but the sum, you have to add this one, and you have a small increment added because you get this averages out and this average, but this is extra. So this little extra causes the RMS value to be increased, and my spreadsheet gave me that answer. So, conclusion, the AC in AC signals, AC power, whatever, stands for alternating direction of current, not alternating values. But the sine and cosine function were defined to have alternating values, and science likes to use those values. So the standard math right now is easier to use than the math for the particle model. But then to measure AC voltage and currents, a fix was made so that the values would not come out zero. Whereas if we could, it would be great to have a new symmetry math that Jack Kirkendall mentioned in one of David's presentations. If it were completed to a point where I could use it for the AC calculation, I'd love to do it. But I'm not familiar with it enough and haven't used it. So for now, all the math I've done involves standard math. Yeah, it's easier to use. But alternating current does not mean negative. There are no negative particles in the particle model. There are no, the value of the particle never is negative. Its charge is not negative. It's just a particle. And so a negative is supposed to represent direction, not value. My name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask Particle. Email me at particleguru@gmail.com or comment in the video where you just click on the bell and you can add your comment. Thank you for your attention.